I think we're on.
I just got a email saying the front side is live now.
Cool. We are live now, I suppose.
I'm not seeing it yet.
Okay. I think there's a delay on if you're looking at the YouTube page itself. It says 0 viewers, so cool.
Just rewatching.
Well, all right. So today we're going to talk about, we're going to continue where we left off in our first discussion about the blockchain. The goal with that was to kind of, understand what a blockchain was so that we could get to the point of using a blockchain for more than just money. So part one of this presentation, which you can find on our channel, focused heavily on Bitcoin, which is sort of the first modern implementation of a blockchain, at least that became widely used. But the blockchain can be used for things beyond just simple balance transfers. And today we're going to be talking about the Ethereum network, which is essentially a global computer. And so we're going to look at kind of how that works under the hood, and then try to play around with some code running on that global computer, as it's called. So let me see if I can share my screen here. Okay. All right. So yeah, this is part two of blockchain-based distributed applications. So we're going to be talking primarily about Ethereum today. Ethereum itself is not simply a coin. There is a currency associated with it called Ether, but the two terms are often conflated. So Ethereum kind of came to the public in 2015. This guy, Vitalik Buterin, I'm not sure if that's the correct pronunciation. I think he was like 19 at the time, dropped out of college, got some funding, and kind of went with this idea of having like a scriptable sort of Bitcoin. They weren't really sure when they started with it what it would become. And what it ended up becoming was sort of this platform where you could run decentralized applications using or having the same kind of guarantees that you get from the trustlessness of the Bitcoin network. So since we talked a lot about Bitcoin in the last presentation, let's kind of compare them so we can get a footing. So Bitcoin is a decentralized currency. The blocks in the blockchain contain basically just a ledger of of like value transactions, changes of balances for various accounts. Its big appeal is that there's no centralized bank because of the nature of the blockchain. We can trust consensus to bring validity to a given transaction, a given history. Now, Ethereum, is very similar. It is also a blockchain, but there's more in each block than just transactions of balance. There is that, but there's also basically application state. So there's basically, you can write code that can run kind of within the blockchain, which is a very big way to put it. We'll kind of dive into what that means. But as business logic executes within the system, the resulting state changes are propagated back out as blocks on the blockchain. So it kind of ends up looking like one of those graphs that Charles often draws of state transitions. And we have that, for every application running on the network, all over the world is kind of represented within that. So it's pretty hard to wrap your head around. It's a pretty large thing. And so the draw with this is basically there's no such thing as a client. There's no such thing as a server. All nodes that are on the network are participatory in one way or another. and therefore things, applications that are run on this network are immutable. They're immortal unless they kill themselves. They are, unable to be censored. They're unable to be shut down. There's no, server where a disk could fail. There's no downtime really, because, there's always going to be kind of another person's machine that can execute the code. So you can kind of think of it like BitTorrent. If you're familiar with BitTorrent, everybody hosts sort of small chunks of a given file, and you have like a swarm of peers that you can get that from. And so this is kind of like that, but with computation. Let's see. All right. So yeah, you don't use a normal browser to visit a DApp, which I guess I should clarify. A DApp is a decentralized application, which is also sort of vague, but it's an application that is run on this Ethereum network. Obviously, you need more than just. I mean, if there's no client and no server, a web browser isn't really what you're using. So what you use is a piece of software that's kind of like a combination of a wallet, a server, a virtual machine, and a web browser all in one. The most common of which is called Mist. So yeah, you're constantly serving information back to other peers on the network, and that's sort of part of the cost of entry, I guess. Yeah, so it's transactional. The way that you interact with it, works kind of like a database transaction, essentially. Like you send off a request into the network and say, hey, I want to process this, thing. I want to pass this value to this chunk of code and execute it and persist the response in the blockchain. And while that transaction is taking place, the resources involved are not able to be touched, so we avoid things like race conditions. It's immutable. Once you have a contract up, it's up forever. And even, if it is taken down, the history of it will always be there because of the nature of the blockchain. There's a record of everything, and everything is transparent, down to code execution, down to variables within the code. Everything can basically be seen by the public if they look hard enough. And that's a very interesting facet of this ecosystem. You have to be, very careful, I guess, about, how you write your code. In fact, I think it was either earlier this year or maybe over a year ago by now, there was an exploit, against the Ethereum network itself that was able to siphon off like $50 million worth of Ether. So yeah, you have to, use some patterns that are not, necessary or common in sort of regular software development, which makes it interesting. So, all right, so it's a global computer, right? What does that mean? Where is the computation taking place? What operating system is the global computer running? How does any of this work? So we're going to just kind of go through this glossary. We need to get our heads around the terminology basically associated with this, and there's a lot. When I first started digging into Bitcoin, I thought it was relatively complex. This blows it out of the water in terms of what is going on in the network to make this all work. So yeah, I'm gonna do my best to explain it, but certain terms are involved in the definition of other terms. So like you're going to hear terms from this list used before they're really defined. There's not really a linear way to lay it all out. So a node is, a piece of software participating in the network. So that, browser-ish thing that's also a wallet and a VM, that, represents a node. There are client nodes, which are basically, they keep a copy of the blockchain and they listen to transactions and verify new blocks that are added to the chain. And then there are mining nodes, which we'll get into later. But if you remember from Bitcoin, mining nodes are responsible for minting new blocks for the chain. And so, an actor is an entity, basically you. It's usually a person capable of interacting with the network, but not living on the network. You don't live in a block on the blockchain. You live wherever you live. But it's important to make the distinction between an actor and an account, which does live on the blockchain, because actors can have multiple accounts and multiple kinds of accounts. So an account is really the most important kind of thing to grasp here. And an account is sort of the mechanism by which the network is exposed and interacted with. If you go to a website, you might type in google.com. On the Ethereum network, you're going to be going to the address of an account, essentially. There are, all accounts are basically state objects. They have an amount of space on the nodes, like physical machine allocated, and so all of those state objects have kind of like certain common attributes, one of which is a balance. And we'll get more into that later, but there's sort of, just like, that's what the wallet part of the node is, that you have a balance of whatever, and so each transaction kind of involves balance, value changing hands. And, you also have a key, and the key basically a key pair. So you generate RSA keys and you keep your private key, and then your public key is through some algorithm translated into what becomes your address. So all traffic in and out of an address, is signed to verify kind of the identity of the account. The way accounts interact with each other is these transactions that we've talked about. So yeah, they're signed. They contain data for consumption, or simply a transfer of balance. And it's interesting to note here that if you remove, if all you allow transactions to do is kind of update the balance within the state of different accounts, then you have a cryptocurrency. And so actually, writing your own Bitcoin in Ethereum is a matter of maybe 25 lines of code or something, because yeah, that's all it does is kind of just plus and minus. So there are two different types of accounts, and this is sort of where it gets interesting. There's the externally owned account, which I guess, I hesitate to put it in these terms, but you can kind of think of these as a client and a server type of account. An externally owned account is a sort of like a client. Basically, all you have is a balance and a count of transactions associated with your state. You don't have any executable code associated with the account. It's pretty much just, you're browsing other applications. But then the accounts that are more server-like are called contract accounts, and they hold smart contracts. So in addition to the balance, and they have a balance of their own, they have executable code, actually bytecode, but yeah, like an instruction set, and then also there's application state. So when you're a contract account within the state, within the storage that is allocated for your account, a sort of activation record is created where you have basically the equivalent of like a stack and a heap. And it's you're able to kind of run code within that context. So how, what is that code? How does it run? Basically, there's this Ethereum virtual machine, and it's a runtime environment present on every node. So that might give you a little pause, right? To think that whenever a contract is sort of executed, it's doing it necessarily, doing it on your computer a lot of the time, and we'll kind of get into that more in a bit. But the EVM, was designed to be very, very tightly sandboxed. So there's, little to no chance of code escaping it and messing with the host machine, or at least that I know of. There's been no occurrence of this yet. And they're even sandboxed from other contracts that are running. So they can only really communicate with other contracts if they're like explicitly allowed. So security at that level, as far as code that is executing on your machine, is very good and very strict. So, one last thing about the virtual machine. If you think about it, as a node, part of what you're doing is processing these instructions on your EVM and verifying that the state changes associated with that execution have been correctly persisted to the block that has been added to the chain. That means you can see the source code, you can see the execution, you can see who is issuing the execution, because all transactions are also state. So everything's very much out in the open. Now, balance is something we've kind of glossed over, but basically, the cost is distributed as well as the computation. So when you think about the internet as we know it today, there's you pay an ISP for access to the internet. You pay if you're a host of a website, you pay for server space, or you might even pay a company to manage your server space. In the Ethereum network, there isn't any centralized point of that, so there's no real hierarchy of value. So the value transfer is also kind of done on a peer-to-peer level. And because the burden of storage and computation is distributed among the peers. So gas is this concept, it's basically what a contract needs to run. It's the cost of computation, but it's not tied directly to a currency. Gas can only be paid with Ether, which is a cryptocurrency. However, the cost of that fluctuates. So the cost of computation isn't getting dramatically more and less expensive. Gas is kind of an abstraction that lets you keep the real value, so to speak, of computation relatively constant. So gas cost is like the real computational cost involved, and that's actually set at the level of virtual machine instructions. So certain instructions are assigned a cost, the costliest of which is setting up a new contract on the network. And this cost, there's no way that you can adjust it as the creator of a contract. You can't say, I'm going to create this code and you have to pay me this much to execute it. It's not a market. You really need to think of it like a fuel that is being burned. So to offset that, there's this concept of gas price in addition to the gas cost. And so when you run, when you issue a transaction to run a contract, you're going to pay in Ether the gas cost multiplied by the gas price. So it's adjusted for kind of the market at that time. Now the really important part of this is that
the gas cost, though. Who sets the gas cost?
It's set at the creators of the protocol, essentially. So it's set. It's like hard tied to a step command or whatever execution, whatever instruction is being executed has an inherent cost associated with it. And I think it can be changed by the administrators of the network. I think at one point they changed the cost of issuing a new contract, but for the most part it's relatively static. And then because the language that the code is written in is static or statically typed and compiled, you can kind of determine the real cost ahead of time. And then the price is sort of, I don't know, it's set by it essentially, and that's kind of the important part of this. The price is sort of the equilibrium of how much users are willing to spend and how much the processing nodes are willing to accept. So you can issue a transaction to a contract and say, I'm going to pay nothing. And that's totally valid. It may never get processed, but it's totally valid. The more that you spend on a transaction, that kind of higher priority that transaction is going to get for computation. So it's like a market demand that drives which transactions get processed first. And that's, we're going to touch on that again in a minute, but that's sort of the most important thing to know about gas, I guess. So a transaction then is, it's a data structure with the following elements. There's the address of the intended recipient, the identity of the sender, which is the result of it being signed by their key. There's an optional payload of data as input for the contract. There's a value field, which indicates the amount of gas that the sender is providing or offering to fuel the computation. And then there's a field representing the maximum amount that the transaction is allowed to take of gas. And there's the gas price value that goes along with every request. And that's where we get to, what I was saying before. You have the ability to kind of set that to whatever you want. And yeah, so gas is usually paid in WEI, W-E-I, which is the smallest denomination, like metric, breakdown of ether. It's 1 quintillionth of an ether. And it's totally arbitrary by the sender. And, so who collects that fee? Who decides the order in which these transactions get processed? We're talking about, you can increase a gas price for a given transaction and receive preferential treatment, essentially. Preferential treatment by whom? That's where the mining nodes come in. So a mining node is a special node that is capable of publishing new blocks to the chain. We talked about this in part 1, I believe, a bit. You can mine Bitcoin. It's essentially the same type of thing with Ethereum, where you are racing against other miners to kind of solve a very difficult puzzle. And that's called a proof of work. So you're, kind of verifying, I guess, a block. And when a miner, cracks a new block, the block comes down, and it's broadcast to the rest of the network that, hey, the next block has been minted, so stop working on it, move on to the next one. And then the miner who has minted that block selects the transactions that are going to be included in it. And so the transactions, usually, that's based on, the gas price that's being offered. But, you gather, maybe 20 or whatever different transactions from all different kinds of users that have been broadcast to the network, but not yet persisted into the chain. And then the mining node within its EVM, within its virtual machine, runs all of these transactions, computes the resulting state, which again is a global state. When it's namespace obviously to these contracts, but when you think about it, like it's computing state for the entire machine, the entire network. And then once it has that state computed, and the new state is arrived at, then it's signed with the proof of work, or rather, combined with the proof of work and signed by the miner, and then the new block is broadcast up to the network. Once it's broadcast out, all the other nodes who are not mining nodes, the average users, have to verify the validity of this block by running the code themselves also. So, the way mining works is that it's very hard computationally to create a new block, but it's supposed to be very easy and fast for peers on the network to verify a block. So once this block goes out, there's, say there's 1,000 people listening, the code gets run 1,000 times. And if the code is, not like, if the resulting state is not agreed upon, you go with the state that is agreed upon by the majority of the peers in the swarm. So that's where that consensus of trust comes in again. But I mean, that's quite inefficient, right? You're running your code on thousands of machines. There's all this communication going on, and brokering and whatnot. There's, it's not great to run code on this thing. The more I researched it, the more I realized it's not a magic bullet at all. Oh, by the way, this is what it looks like. Everything they just described roughly comes out to look like this, which is kind of mind-boggling. I think our diagrams for Bitcoin were just kind of little boxes with arrows, but yeah, there's a lot going on in the Ethereum network. So anyway, it's not, we can't make all apps, DApps and make them, like super trustworthy and secure. In fact, security, is kind of a concern. Like there's a lot of security issues with running your code on thousands of people's machines. What it's good at is, problems where trust and transparency are super important. Using this network, governments could feasibly implement internet voting because, you have the ability to identify voters, you have the ability to hold a history that cannot be tampered with, and all of the voting is done, you can see all of the voting and the vote tallying, because everything is kind of happening out in the open. So it's, something that, we often wonder why we don't have it. The answer is usually, it'd be easy to hack, but with, the application running on a system like this, it would be impossible to hack. And so, that's one major application that I doubt we'll see anytime soon, but, could be implemented today, basically. Finance, anything where large sums of money are involved. There's a lot of gambling platforms that are built on Ethereum, lending, escrow, stuff where, you want a clear record of what happened, and you can do things like don't release this money to to the person who wants it until 2 out of the 3 people in control of it sign off or something like that. It's very good at that type of stuff. And then the other thing that's kind of interesting is this crowdsourcing side of it, where you can now monetarily incentivize stuff, just anything. So there's a Gitcoin, right? There are DApps that will basically, you can put a bounty on an issue, on a GitHub issue, and then the person who makes the pull request and gets it merged gets that bounty. So it's kind of a way to make value, the transfer of value and property more peer-to-peer. It sort of undermines the current systems that we have in place for managing things like that, in the same way that Bitcoin undermined banking. The other thing is that you can very easily write your own platforms on top of the Ethereum platform. I think I mentioned earlier, it takes 20, 25 lines of code to create your own coin. So a lot of places essentially do that. It's sort of like Disney dollars, right? We're going to have a gambling platform. There's for instance, Augur, right? Augur is a gambling platform, or I'm sorry, a prediction market, as they call it, where essentially you can, bet value on the outcome of any given event that you could imagine. But part of that system is you buy Augur, which is distinguished from a cryptocurrency in that it cannot be mined. It's based on the Ethereum network, so you buy it with Ether, but it's specifically meant to be used with the platform that goes with it. And so those are called tokens, and that's becoming this kind of burgeoning, field, I guess, within this sphere right now. Tokens can also represent stake in a company. So right now we're seeing this, large amount of ICOs, initial coin offerings. So if you have a service, a decentralized service that you're going to be running and you want to fund it, you set up an ICO where, people can pay to buy tokens for your system at a low price, hoping that if the system becomes popular, then the tokens, become valuable. And, that's been the case a lot of times. Ethereum itself was funded through an ICO and, started out at less than $1 and now we're worth $300 a pop. But there's also, a lot of kind of, scammy bullshit ICOs. I mean, there's a dozen every day you could go find. So that's, using those tokens, those unminable kind of pieces of value that are specific to a platform, allows these, new platforms to take place. So really that's where Ethereum has really shined. It's a platform for platforms. The other really interesting avenue for this is the Internet of Things. We touched a little bit on this when we had one of our podcasts about IoT, but there's something fundamentally off with the way that we're handling IoT currently. We're writing a lighting solution for our office. We want to be able to control the lights, securely and kind of dependably through internet interaction. And we're using AWS to store state for these light bulbs. And if it's an Internet of Things, there's something that feels kind of just off about having the central, having a central point of truth, having basically a dictator of the light bulbs, where it's always right and the devices have to listen. What kind of makes more sense is if the devices could sort of rely on each other for information, and that leads to truly decentralized Internet of Things, and you're able to have an Alexa or something that's not constantly phoning home to Amazon, telling them what you're interested in. If you say, blockchain Alexa, shut down the oven, it'll just talk to the oven and do it. So in IBM in 2015, this is before Ethereum was even publicly available, IBM published a paper using the Ethereum blockchain as a registry for things and events, and then they used contracts on the Ethereum network to define sort of rules of engagement between devices, and then Bitcoin and telehash for communication and persisting state. And they were able to kind of make this network of appliances that depended on, they were interdependent in a very profound way. Larger appliances like a refrigerator or a washing machine, that are capable of maybe more computation or more memory, kind of accepted the responsibility of holding larger portions of the blockchain, whereas smaller appliances, were more based on peer-to-peer communication. What developed over time was that the devices, started trusting, the level of trust would increase over time for reliable, nodes within the network or whatever. And so they sort of cooperated in this very organic way. And, when we're talking about a potential future where there are self-driving cars, I think, having one source of truth becomes an anti-pattern. If all of Chevrolet's self-driving cars are kind of in touch with a central data point, or a central service from Chevrolet, and somebody gets, their malicious hands into that service, you have this massive implication of, an exploit. Whereas with this kind of decentralized model where we use the blockchain in such a way that devices can learn to trust each other, a car that receives a command to drive off a cliff can ask a passing car, hey, should I drive off this cliff? And kind of see the history, see the correct blockchain that says, no, please don't drive off this cliff. So that's, I think, it's going to take a while for the technology to catch up, but for IoT to really be successful and not truly horrifying, we need to be leveraging peer-to-peer technologies like this. All right, so that's a lot to take in. And I boiled it down a lot, believe it or not. There's, that's a pretty minimized version of the reality of the complexity that's at play here. So if you want to write a DApp, first, you kind of have to understand it. And that's really, maybe the hardest part. Second, you have to buy Ether because you have to be able to, deploying an application, deploying a contract to the live network costs money. And then running it, every contract has its own wallet of money, right? So running it, also costs money that, you're collecting from the clients, but still you need, this initial kind of investment. And it doesn't cost much. It might cost $1 or something. I think it's 5,300 Wei, which I don't know what that comes out to in US dollars, but it's next to nothing. It's generally these microtransactions, but you need it, you need to understand the risks, which really not even, the creators of Ethereum, I think right now fully understand. There's so much in the way of security implications with running code in this distributed way. I think as, if the platform becomes more popular, as it becomes more popular, we're going to see, just like there are way more viruses for Windows machines than for OS X machines, I think, the more popular this becomes, the more open to security vulnerabilities it's going to be. And, we don't have very clear, we don't even have a clear idea of what this is currently, let alone some type of, penetration testing or any type of infrastructure for security. There's a small wiki article on their GitHub page of, best practices. That's about it as far as security is concerned. So to the best of your ability, it's good to kind of be very conscious of making your code secure and using access control. And then finally, you need to kind of actually learn about the technologies involved. And there are a lot, and there are more all the time. Solidity is the primary one that you should probably know about, that you probably haven't heard of before. It is a compiled language. It compiles to the bytecode that is then run on the EVM. There are other higher order languages for the Ethereum network. Serpent is one that's based on Python, but Solidity is by far the most popular. And so you need a Solidity compiler to be able to compile your contracts and migrate them to the network. Web3 is a JavaScript layer that allows you to interact with these contracts. Web3 is, kind of a take on the idea, we had Web 2.0 already, and this is, kind of the next iteration of that. So basically, any web application that is talking to the Ethereum network, Web3 is the way that it's doing it. So Swarm and IPFS are really interesting. These are data stores, very similar in practice, but different in philosophy. But essentially, it's, you can think of it almost exactly like BitTorrent. You are able to place files from your computer onto kind of this global file system with one command from the command line. And then those files, when somebody goes to get them, are either, if they're already present on your machine, you get it locally. And if they're not, you go to somebody else's machine to get it in the Swarm. And basically, files are identified by their, I think, SHA-256 hashes. So it's instead of an IP address, you just say get and then a hash, and it can automatically know which file you're talking about and who has it. So Whisper is a messaging protocol that is still very young. but will allow for kind of better communication between services, and also communication that takes place off of the blockchain. So, if you have information that you need to kind of convey without having kind of the movement of that be visible, Whisper is coming along to help with that process. Now, Truffle and Embargo are the two sort of frameworks that have emerged for spinning up a DApp and writing a DApp. Truffle is the more kind of preferred by the community, and that's what we'll be messing with in a little bit. And MetaMask is a it's a Chrome extension, and it's also built natively into the Brave browser, where it builds that wallet functionality into the browsing experience for you, so you can convert your regular Chrome into something that is able to use the apps with MetaMask. Okay, so let's, I guess, look at some code. Well, I wonder if I can. I'll bring this down here, I guess. All right, cool. All right, so this is some stuff that I've been hacking on. Not currently working quite, the way that it should be. Also, is that maybe I should make that text a little bigger? Yeah. Let's see here. How's that? Is that any better? One more?
I had to reload.
One more.
All right.
Can you zoom into a part of the page?
I don't know.
There's Commission plus your work.
Yeah, no, it's zoomed in now. Yeah. See? So, yeah.
That's better.
Right. So this is, on the left, we have some Solidity code. My idea here was to kind of implement payola, which is, the practice of paying DJs to play certain, musicians on the radio. So basically all it does is, you send an amount of, coin to the service. And if that amount of coin is greater than the current highest amount, your name gets put up on the board, basically. As you're now playing on the radio. And then otherwise, it's kind of a no-op. So yeah, that's sort of all this app is supposed to do. You can get a kind of a feel for what Solidity looks like. We have events that can be listened for by other contracts and by client code, like this JavaScript over here. And then, yeah, functionality, implemented here that kind of takes a record in from the outside and acts on it. And so when you compile this and migrate it onto the chain, it starts off with, this kind of nil state or whatever. You do have the ability to, use a constructor within Solidity, but this didn't really need it. And yeah, when somebody sends a message, for instance, here I'm, calling this become radio star method with my own name, and from, the first account in the kind of test setup that I have, and then I'm passing 10 gas or whatever. I'm not actually sure if this is gas or if this is ether or, a denomination of ether, but you pass a value along, and then message is kind of that structure, which, you have message.value, which is sort of the, price that was paid, and then also message.data. So you're able to kind of take things in like a name here. So for instance, yeah, this expects as an argument. So that's why this is not in the hash. This expects a string, and then it sets, it sets that. So yeah, this works or was working earlier. I can spin it up. First, I think I'm actually going to kind of just go through the setup of how you even get a development environment running. Let's see here. process. No. Okay. So here, I guess I can make this a little bigger also. Is it relatively visible? All right. So I spun this up using Truffle. And Truffle is one of the frameworks, a little bit bigger, like a Rails type of thing, where it's it's a command line interface and also kind of a framework for how a DApp should be laid out. I can use Truffle to initialize a new application. I can do Truffle init, and in fact, I think in this case, what I want to do here, just to show a base case, is unbox the React thing. So Truffle has this concept of boxes, which are sort of like skeletons for a developer environment. All of them have smart contracts, but they also include other code. And so one of those is React. You can spin up an environment with this unbox command that sets up a basic contract and some basic client code using Web3. So just setting up a a base version of this. And while this is spinning up, let's take a look at.
Is Truffle actually written in Ethereum or Solidity?
I think it's JavaScript. Yeah, no, it's definitely JavaScript. You install it with npm.
Okay.
Yeah. Yeah, I'm not sure. I don't know what would happen. Like, I guess you could write Solidity and then kind of just distribute it as a regular application. Like, you could use an Ethereum virtual machine to run stuff arbitrarily that's not connected to the network. That might be possible. I'm not sure. In any event, let's take a look real quick at MetaFox. So this is, I think, built into Brave now on the most recent releases, but as a Chrome extension, it allows you to connect to different networks. The main Ethereum network is, the main Ethereum network. That's where things are published. But there's also sort of test networks that are less secure, but are designed for, testing things, without having to pay like the actual fee of setting it up on the Ethereum network. And that's important because if you had to kind of deploy something that costs money to deploy it every time you need to make a one-line change, that would be a little less than ideal. And in addition to these test networks, you can connect to your local host on the standard port is 8545, but you can spin up this test RPC client, which is kind of what all this output looks like. And when you create your MetaFox account, it'll give you kind of a recovery phrase, one of those like 12-word long things, and that'll allow you to recover your account. Now, this is a fake account. I don't really have $3,000 in it or whatever, but using this test RPC package, I can spin up a sort of a fake, like a mimic blockchain on my local host using this phrase, and MetaFox will basically understand that it's connecting through this. So I'll spin it up, and you can see it creates 10 kind of bogus accounts, and then something is querying it right now, so it starts logging out the RPC calls. So wow, this is still going, huh? I'm not sure what's taking so long with that. I guess I can spin up the app that I currently have. So let me just, again, not sure if this is gonna, whoa. Huh. I'm not sure if this is gonna work because I've been actively hacking on it right up until now, basically. But yeah, so we have our blockchain running. This also will automatically mine a new block at a given interval. So like normally when you make a transaction, you have to wait for it to verify in the network. So it's slow. But with this test thing, not only do you not have to pay any real money, you also you get instantaneous kind of results, almost as if it's just a regular server. So wow. So let's see. Nope. So this is the project that we were just looking at. So it comes with contracts. So this is based off of the box that we're attempting. Oh, here we go. Okay. Okay. Yeah. So this spun up a new one. I'll run this just because we're sure that it works. So the first thing that you need to do is compile the Solidity contracts. And you can just Truffle compile. Those contracts are located in this contracts directory and have this sol file extension. These, when they get compiled, wind up in an artifacts directory as I think JSON blobs or something that can then be imported by Web3, and that essentially all that does is provide an API. The contract needs to say, hey, these are the methods that I have, and this is how you call them. So yeah, it wrote these artifacts. Once you have the contracts compiled, you just call Truffle migrate. And right now we just see this polling going on, but once we spin this up, deploying an application is actually sending a transaction where you send it to a special block or account where the first number is 0. And all that account does is, spin up new contracts. So you, instead of, deploying a contract, so to speak, you give it code that when executed results in your code. So I just migrated these contracts, which is, I guess, just the simple storage contract, onto this network. And it, ran the transactions and minted 4 blocks to the chain to account for those state transitions. So let's see. Then it's as simple as npm start to spin up. Spin up a web version. So now, all this is doing, right? I think if we look at the contract for when I just created, oh, this is a test. All right. So all this does is store, a piece of data, an integer. And so where'd it go? But because my MetaMask is connected, you'll see this this transaction confirmation pop up. And here I can set, my gas price. I can set gas limit. Because this is a test environment, I'm transferring 0 actual Ethereum or Ether, 0 actual money, but it'll kind of show the gas cost of the transaction. The JavaScript associated with this just displays the value that is being stored. It also, let's see. Sorry. All right. Yeah.
So wait, so it's kind of blowing my mind a little bit. This simple storage is actually persistent this is contract. Simple storage is to store a uint on the Ethereum network.
Yeah.
Okay, so the price there is 37 cents.
37. Where'd it go? I don't believe that's US dollars. That's oh yeah, 37 US dollars. Wow, it's pretty expensive, huh?
It is pretty expensive. I mean, it's still, but price aside, that actually wasn't my kind of like, it was like, wait a second. That's the code
Yeah.
to store a value?
Yeah.
Like, that's pretty incredible. Like, you're basically, it's like, I mean, it's almost like you're storing a closure variable.
What's a closure variable?
It's just a free variable that a function references. Like, it's a variable that's in scope when a function is defined. So when you define a closure, like say like x equals 1, and then I return some function, well, the function can reference x.
Okay. So
that's pretty incredible.
yeah. No, it's neat. Now
Store data equals x, and yeah, okay.
So of course this is only my test instance, but if I were to put this on the network, this would, live forever at an address that you could always get at, so you could always just forever keep persisting this data.
So now when you do the simple storage, I'm going to try and talk loud so I can get on that microphone over there.
Yeah.
When you use the simple storage, now I put the contract out there, and that's $37. But then actually getting and setting, how much does that cost?
I think that's actually the transaction that we're seeing here. And again, that's based on what I'm offering, right? So I can offer less, offer even, 0.
0 gas?
Or I guess in this case, it must be greater than 0.1. So yeah, I could, offer this much for the transaction to be processed, and it might eventually be processed. It's just a matter of how badly do I really want to store this value. I could offer $1,000 and be picked up right away.
So that, yeah, I see. So that that get and set. So the gas price is determined by the number of bytecodes that are contained inside those operations.
Yeah, it's
Right, so that
yeah.
stored data assignment, that's got a gas price.
Yeah, like the set or the variable assignment, I guess.
Okay.
It's like the the machine instructions, which there's a table of it somewhere where you can see kind of each one broken down.
Right.
I think a get even is 0. Like any type of retrieval is 0, but like any type of manipulation incurs some 1 to something cost, with the highest being deployment, which is like 5,000 or something.
So deploying this contract is 5,000?
5,000 gas.
Which is pretty expensive. Like we're talking thousands of dollars now.
No, not at all.
Like 20 gas here costs $37.
Yeah. So.
Oh, I see.
So this.
I see. Never mind.
I guess I don't think it's actually showing on here what the real gas cost is.
Yeah, we have a gas price, but we don't have a gas
Right.
cost.
So you have the ability to limit it, saying if the computation takes more than this amount of gas, just roll it back. I don't want it. And you have the ability to offer, per unit of gas, this is what I'm willing to pay. And I think, under the hood has the ability to basically query and ask how much gas is this going to take. But it's just not being shown in this window. Yeah. And so here's another. This really blew my mind, because you also have a copy of the Ethereum virtual machine. There's 2 ways you can interact with this. If you want to do something that has side effects and persists data, you can send a transaction. But if you just want to compute the result of something, you can run it locally. So you have the ability to just, it's kind of the difference on these 2 lines of code, is that, in the set, you're passing a transaction from an account. And then with the get, you're just computing this on your local machine based on the state that you have already in the blockchain. So does that make sense? Yeah. So this incurs no, cost. Yeah.
Interesting.
So yeah, looking at the code, all this does, there's no real business logic to it. It just, sets the value to 5 with a transaction from one of these 10 fake accounts that were spun up. And then this get is locally computed. So the result of a transaction, is asynchronous. You send it and you wait for it to be picked up and packaged into a block and sent out to the chain. And there's a new block created, I think, every 19 seconds roughly. So while you're waiting, you use this promise architecture. And until you get the result of this back, you're not running anything else. Now, considering that by the time you hit this line of code, you have the result in your state, you're able to use this call to just run the code locally. And in this case, of course, all the code does is return that state. But you could, run like a fairly complicated process, given that you have the most up-to-date state, and compute a new state without, like, the only downside of that is that you're not persisting it back to the, the chain.
Right.
But yeah, it's, a big performance boost. So all this demo does is set that, get that, and then set its internal state and display it. So you can see right now it's 0 because we haven't, made any type of transaction. So I'm going to say, let's spend 18 cents on setting and getting this value. Oh, I might have waited too long there. Let me try this again. Doesn't appear to be going through. Yeah, it's pretty finicky. Like, I've been messing with this for a little while now, and it's not been very reliable. At least with this local machine. Yeah, so we can see there's no actual transaction going through because there's no blocks being minted by the test service, which is interesting. Yeah, not really sure why that is the case. Oh, actually, this could be it. Oh man, this thing is also pretty annoyingly buggy. Well, yeah, no luck with this. I guess I'll try spinning up the app that I was working on. See if we have any better luck there, but if not, that's the way the news goes. So yeah, it's a pretty weird setup. And it's kind of mind-boggling when you think about 675. When you think about kind of the level of complexity that it's currently being used for. They're really complex platforms being built on this, and it kind of blows the mind when you actually, it's just running a simple hello world is quite difficult. So in this, say, going back to the Payola app, I just got this working, 5 minutes before the demo. So if it doesn't work, I'm going to be pretty pissed. Let's comment this guy out. Oops. So I didn't get to the point of actually implementing a form where you can input your name to be played on the radio, but similarly to just the basic test app, to get it to the point, let's see, where the logic actually kind of functions. So let's see. compile my contracts. Okay, and I migrate it. Let's see, we got, yeah, we're running. Okay, and let's see, it's starting up. All right, now here we can see we're in the first instance. We have our contract. Here I'm going to pay 77 cents to become. Oh, failed. Huh. Yeah, MetaFox not liking me today, but yeah. Huh. Yeah. Well, yeah, not our luck today. It got at least as far as setting up the Web3 instance, which maps kind of the back end. So it's been a little while now. I'm going to leave this where it's at. Just take my word for it that I had this working a minute ago. And I, I will probably have it working over the weekend in an actual form. And I might go as far as just deploying something on the network for the sake of, leaving my mark. And for a nominal fee, so can you. So yeah, this is a very weird and very kind of confusing technology, but it's also one that I think once people start to wrap their heads around it, it's going to be kind of a flashpoint. Microsoft already has kind of Ethereum tools that it's building out. Like I said, IBM was using it as early as 2015. It has a lot of potential. So it's probably best to get somewhat familiar with it now. Here's hoping it gets easier to use in the future. Because until recently, this framework, this didn't even exist. So setting this up from scratch would have been pretty rough. But anyway, yeah, that's all for this. So, are there any questions? I guess, hold on a sec. Let's see. Yep, nothing in the chat. Anything either of you want to ask?
I asked all my questions.
Okay, good, because that's about as much as I could answer.
All right, well, thank you, Joe.
Wait, were you going to say something? Oh, I'm sorry. Yeah. All right, cool. All right, thanks, y'all. Clapping for broken code.